So this is the good stuff. This is when we actually get to make some polar graphs. I want to just give a little quick introduction here, and then the rest of it I'll do on the whiteboard so that you can see what these things look like. Now, you got a couple of options when you go to make a graph for a polar equation. One of them is that you can do, remember when you first learned to graph like y equals 3x plus 5, and you made a little t-chart, and you put the x values in, you got out some y values, and you made your plots, and then you connected the dots. You could certainly do that, except this time you would be inputting angle measures, and you would plot the output, which is the radius. So you put in the angle measure, get out the radius, and plot those r's and thetas. The danger is if you don't have some idea what the graph looks like, or if you don't use enough points, you may end up connecting those dots in a way that they were not intended to be connected, and you end up with a very different looking or very incorrect graph. So the way that I'm going to show you is by looking at those corresponding graphs in rectangular form and using that to get the information about the radius of the polar graph. Now, at the beginning, it's going to look kind of tedious because I'm going to have to show you every detail the first time we do it. And then after a while, you'll start to realize how these things work, and you'll be able to draw out your graph, see what the radius does, where it's increasing and decreasing, and from there, you'll get a nice plot of your polar graph. And there are certain types of polar graphs that are somewhat famous, and we'll take a look at those too. So this is the first one. We're going to graph r equals 7 minus 7 sine theta. Okay, the radius of the graph is going to be 7 minus 7 times the sine of the angle. So we can put in a bunch of angles, but you might have to start with like pi over 24, pi over 12, and so forth until you get to enough points that you can see what this graph looks like. So I'm going to look at the corresponding graph of negative 7 sine x plus 7, because you realize what I did is I took the theta and I replaced it with an x. So it originally would have read y equals 7 minus 7 sine of x. But I said you're probably more used to seeing it in the form of negative 7 sine of x plus 7. So I just took the thing that was in rectangular polar form and turned it into something that was in rectangular form. So here, let's switch back to my whiteboard so that I can graph these things. So we said we're going to look at the graph of y equals negative 7 sine of x plus 7. So now this is going to bring back memories of graph translations. Let's start with plain old sine x, right? Y equals sine x. We know that's a graph that goes to the origin. It goes up, it goes down, it ends at 2 pi, right? It starts at 0. Here's pi and 2 pi. All right. What does the 7 do? The 7 changes the amplitude. So instead of it going from negative 1 to 1, now it goes from negative 7 to 7. Okay, so I've taken care of the 7. How about this negative sign that's in front of it? Well, the negative should flip it over the axis. So flipping it over the axis, instead of it going up and then down, this one will go down and then up. All right, so now it starts at 0, it goes down to negative 7 first, and ends up here at positive 7. Still crosses the axis at pi and still ends over there at 2 pi. It just goes in the other direction. Now, what does the plus 7 do? The plus 7 shifts it up 7 units. So now my graph looks like this. Instead of starting at 0, it actually starts at 7. Okay? It comes down, goes up, and comes back down again. I need some important points. One important point over here is pi. That's where the graph crosses what I'm going to call the midline. It has a minimum of 0, but once I push that 7 up 7 units, now it comes up to a maximum of 14. Hits the bottom here at pi over 2, hits the top here at 3 pi over 2, and then ends over here at 2 pi. Next thing I'm going to do is I'm going to make myself a list of all of the things that this graph does. Now, what I've really done is I've graphed the radius of my function that I'm trying to graph. So if you come up to the beginning point here at theta equals 0, the radius is 7. So the radius is 7 when theta is equal to 0. Then what is the radius doing? The radius is going down, right? It's coming down until it gets to 0 when? So the radius decreases to 0 on the interval from theta equals 0 to theta equals pi over 2. Okay, then the radius starts picking up again, right? It goes up, 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 up. I'm going to break this into two pieces. The radius increases back to 7 on the interval from pi over 2 to pi. All right, what's it do from there? It keeps going up, right? Keeps going up until it gets to 14. So the radius increases to 14 on the interval from pi to 3 pi over 2. After it gets to that maximum of 14, it starts coming down again. So the radius begins to decrease back to 7 on the interval from 3 pi over 2 to 2 pi. And because this is periodic, I know if I do it again, I'm just going to end up with the same thing, except it'll go from 2 pi to 4 pi, 4 pi to 6 pi, and so forth. So I've made myself a little map. The radius starts at 7 when theta is 0. It decreases back to the pole, right, back to having a radius of 0 from 0 to pi over 2. Then it increases, and it decreases again. Great. What on earth am I trying to graph? Let's take a look at it. Let's make ourselves a set of axes. And remember that we're graphing the radius. So here's theta equals 0. Here's theta equals pi over 2. Here's theta equals pi. Here's theta equals 3 pi over 2. And when I come back to the end, 0 will be the same thing as 2 pi. So it starts with a radius of 7 when theta is equal to 0. So in the direction of 0, I'm going to go 7 units, and there's a point. Now think of these radii as sort of the spokes of a bicycle wheel. Here it is with a radius of 7. The next radius is going to be a little bit less than 7, so maybe its next radius is 6.5. Then the next radius is going to be a little shorter, that'll be 6. Because we said it's decreasing to 0 by the time it gets to pi over 2, then it's decreasing to 5. What is happening here? I'm creating a curve that's working its way in until it gets to a radius of 0 by the time it comes here to the origin. All right, so that's the radius decreasing to 0 from 0 to pi over 2. Now, from pi over 2 to pi, the radius is going to increase to 7. But 7 in which direction? 7 in the direction of pi. 7 in the direction of pi is that away. So we would think of it as negative 7. All right, so I've got another set now that's increasing until it gets to negative 7. Now it says it increases until it gets to 14. But 14 in which direction? 14 in the direction of 3 pi over 2. Well, in the direction of 3 pi over 2 is negative, so I'm going to increase until I get to 14. And then the radii are going to start decreasing again. So if the whole thing is 14, the next one will be 13 and 12 and so forth until I get back to a radius of 0. Huh. Look what I made. Sort of lopsided because I'm drawing on a little tablet here, but it looks like a heart. And in fact, that's what it's called. Well, it's not really called a heart. It's called a cardioid. Now, this is something that would be a bear to try to graph using y's and x's, but in polar form, it's not that bad, right? You start with your radius, it decreases, it increases, and then it decreases again. Cardioid, like cardiac, comes from heart, but there are other uses for our cardioid besides just, thinking about your heart. The microphone that I'm using right now to record this video is what we call a cardioid microphone. Look up a Shure SM58. In fact, I'll bet you if I pull up here, let's look at an SM58. That's actually the mic that I'm using. And it says right here, it's a professional cardioid microphone. What that means is if you go back to the pattern that this looks like, it's going to take noise from here, right? This is where I'm speaking, right? This is where my voice is. And it's going to try to knock out the noise from behind it. So, I mean, that doesn't mean it's going to be perfect. I live next to an interstate highway. The windows are open, so you might hear a little bit of background noise, but you're not going to hear as much as if it also picked up noise from the other side of the mic. So if you're a vocalist, if you're singing or you're trying to interview somebody or you're, speaking at a sports arena, you don't want to pick up the background noise. You want to pick up just the noise that's coming from somebody's voice or from somebody's instrument. And so a cardioid mic is best because it would knock out the noise from behind it and only pick up the noise from in front of the microphone. On the other hand, if you're like trying to record a town council meeting, then you want to pick up everything. Cardioid mics wouldn't be good there because whoever's speaking in the dead zone behind it, you're never going to hear them. All right, so that's a cardioid. That's one type of graph that I might want to graph. Right? Are there others? Oh, sure, there's others. Okay, let's take a look at this one. Let's do a graph of r equals 3 times the cosine of 2 theta. Right? What does this look like? Well, in order to figure out what it looks like, I'm going to appeal to the rectangular version of this. So the rectangular version of this is y equals 3 times the cosine of 2x. What does this look like? Well, if we're not quite sure, let's start with y equals the cosine of x, right? That's the sort of parent function. Cosine starts here at 1, goes down and then back up again. It does a complete cycle between 0 and 2 pi, so pi is the piece in the middle there. All right, that 3 in front of there is going to change the amplitude. So instead of it going from -1 to 1, is now going to go from -3 to 3. That 2 that's in front of the theta is going to change the period of the graph. So instead of being on the period from 0 to 2 pi, I'm going to be able to create 2 cosine graphs between 0 and 2 pi, which means now I'm going to end up going from 0 to pi to create a cycle. So this graph is going to start here. It's going to go down and back up again, and then it's going to go down and back up again to go from 0 to 2 pi. I'll bet you if I can figure out what it's going to do from 0 to pi, I can figure out what it's going to do from pi to 2 pi. So now what are the important points? Pi is the top of the graph. Pi over 2 is now the bottom of the graph. Pi over 4 is one intercept, and 3 pi over 4 is the other intercept. All right, so if we do like we did before and go to make ourselves a list of what the radius is doing, this is 3 up at the top here. This is -3 down the bottom here. This starts with a radius of 3 at theta equals 0. Then what does the radius do? The radius decreases from 0 to pi over 4. So the radius decreases to 0 on the interval from 0 to pi over 4. Okay? Then it keeps decreasing, right? It decreases to -3 on the interval from pi over 4 to pi over 2, right? So from pi over 4 to pi over 2, it continues to decrease. And then it increases twice, right? It now changes direction and it increases to 0 from pi over 2 to 3 pi over 4, right? That's where it crosses the axis. And then from 3 pi over 4 to pi, it increases again. Hits a maximum of 3. So it increases to 3 from 3 pi over 4 to pi. And then it's just going to repeat the same thing all over again. So why write another set of directions? Just write them here, right? Now from pi to 5 pi over 4 is going to decrease. Then from 5 pi over 4 to 3 pi over 2, right? All I'm doing is I'm taking all the coordinates that I had and I'm adding pi. So now 3 pi over 2 to 7 pi over 4 and 7 pi over 4 to 2 pi. Well, this is going to be an interesting looking graph. Try to give myself as much space as I can. So we're drawing a set of axes. And let's start with a radius of 3 here at theta equals 0. Now, the radius is going to decrease from here to pi over 4. Sometimes you'll see somebody drawing like a little asymptote here at pi over 4. I'm not going to leave that in there because I've already got enough stuff written on here, but sometimes you'll see that drawn in there. All right, so until pi over 4 decreases. Now, it decreases to -3 on the interval from pi over 4 to pi over 2. So here's what you got to wrap your head around. Pi over 4 to pi over 2 is this piece in here. But if the radius is negative, it's actually not going to end up in the first quadrant. It's going to end up down here in the third quadrant. So from pi over 4 to pi over 2, instead of going up into that first quadrant, it's going to come down into the second quadrant. Right? So it's going to come down here to -3 by the time it gets to pi over 2. Then it comes back to 0, right? This third line says the radius increases to 0 by the time it gets to 3 pi over 4. And then it begins to increase to 3, but 3 where? 3 in the direction of pi. So 3 in the direction of pi we would think of as negative 3. Okay. Great. That's half the graph. The other half of the graph comes from the second column. So now you can sort of follow the pattern. It goes back to 0. It decreases to negative 3, but negative 3 in the direction of 3 pi over 2. Well, 3 pi over 2 is down here, right? 3 pi over 2 is down there. So if it's in the negative direction, you're back up to the top here. All right, so there's my negative 3 in the direction of 3 pi over 2, back to 0, and then back to 3. Huh, what have I made? These things here are not actually part of the graph. These are just my explanations. What does this look like? Looks like a fan blade, kind of, but it's not actually called a fan blade. It's called a rose. And this rose happens to have 4 petals. Turns out that this rose, we said, was r equals 3 cosine 2 theta. That 3 will give you information about the length of the petal, and this thing over here will give you information about the number of petals. If it's even, it's going to be twice the number. So in this case, we had a 2 theta, so the number of petals is double 2, which is 4. If you had an odd number, it would be the same as that number. So if you had a cosine of 5n, or 5 theta, you would end up with 5 petals on your rose. If you had a 7, you'd end up with 7 petals. But if you had 8, you'd end up with 16 petals. So if you really like somebody, give them a rose equation that's got an even number before that theta, and you'll end up with a lot of petals on your rose. And of course, if you change that number before the cosine, then you make your petals bigger. All right, I'm going to tackle one more, and then we'll finish the last couple in a separate video. This one is going to be a little different looking than the others because it's got an extra piece to it. And here's what I mean. Let's take a look at the graph of r equals 2 minus 4 times the sine of theta. Now, just for a little perspective, the first one we did was r equals 7 minus 7 sine theta, which looks a lot like this, except you notice that in this case, these two numbers were the same. In this case, these two numbers are different, and the number before the sine is bigger, and that's what's going to cause the graph to be a little bit funky. It is possible to graph these things the other way around, and to put like a 4 minus 2 sine theta. That's not as interesting, and you'll see why in a second. When the two numbers are the same, that's how you end up with those cardioids. And by the way, if you want to flip those cardioids around in different directions, change the sign before the sine theta, make it positive instead, and you'll flip it. Change that sign to a cosine, and all of a sudden your heart will go sideways. So instead of your heart going up and down, then your heart will go sideways if you change that sign to a cosine. So there are ways to alter these things. All right, let's see what this 2 minus 4 sine theta does. Let's look at the Cartesian equivalent, which in our case would be y equals negative 4 sine of x plus 2. Well, negative sine of x goes down and back up again, right? We had tackled that the first time. Instead of 1 and negative 1, we'll have a 4 and a negative 4. So that takes care of negative 4 sine x. Now, is this plus 2? That's going to be the difference. If I graph negative 4 sine x plus 2, you notice it doesn't clear the axis. It starts here at 2. Right? That's my midline. And then I'm going to go down 4. Up. Way up. Back again. All right, so now instead of it going from negative 4 to 4, it's going to go as high as 6 and as low as negative 2, which is going to create some interesting points. This one over here I can see is pi. This one over here is 2 pi. The point in the middle, 3 pi over 2. So it looks like all the odd stuff is going to happen between 0 and pi. I'm interested in what are these points over here? Where are these places where the graph crosses the axis? Because that's going to be of interest to me. This point down the bottom here I can see is still going to be a pi over 2. So that's not going to be anything weird. It's those two dots in green on the left and the right that I have to try to figure out what those values are. So those are the places where this graph is equal to 0. So where is 0 equal to negative 4 sine of x plus 2? Well, move things over, and you get 4 sine of x equals to sine of x is equal to 1/2. Good. So where is the sine of x equal to 1/2? Two places. Pi over 6, 5 pi over 6. And in the context of our graph, that seems to make sense, right? Pi over 6 goes over here. 5 pi over 6 goes over there. All right, so when we make this list of what's going on, it's going to look involved from 0 to pi, and then it's going to sail along pretty quickly after that. So it starts with a radius of 2 when theta is equal to 0. The radius decreases to 0 on the interval from 0 to pi over 6. Then it decreases to -2 on the interval from pi over 6 to pi over 2. Okay, picks back up again. Radius increases to 0 from pi over 2 to 5 pi over 6. And then it increases back to 2 by the time it gets to pi. So from 5 pi over 6 to pi, it increases. Now, there's really only two other things it does. It increases to 6 when it gets to 3 pi over 2. So between pi and 3 pi over 2, it goes to 6. And then it goes back to a radius of 2. Radius of 2 by the time it gets to 2 pi. All right, so I'm going to squeeze that in the bottom corner of the screen so that you can see what it's doing. So like I said, most of the action happens between 0 and pi. From pi to 2 pi, not a lot happens. Okay, what could this thing possibly look like when I get done with it? Let's graph it. So we said this starts with a radius of 2 when theta is equal to 0. So here is a radius of 2 when theta is equal to 0. It decreases to 0 from theta equals 0 to theta equals pi over 6. And then it decreases to -2 between pi over 6 and pi over 2. Now we're going to run into the same thing as last time, where this thing here is pi over 2. So if it were positive, it would be up here. Instead, it's in the other direction, so it's down here at -2. So it decreases to -2 by the time it gets to pi over 2. So pi over 2 would normally be up on the top if it were 2. Because it's negative, it comes down the bottom. All right, then it goes back to the pole, right, back to 0, and then increases to 2 in the direction of pi. So 2 in the direction of pi is over here. So that's the first half of the graph, and it looks suspiciously like one of those rows graphs. But here's where it becomes different. The radius increases to 6 in the direction of 3 pi over 2. So 6 in the direction of 3 pi over 2 is way down here. Right, that's 6 in the direction of 3 pi over 2. And then it goes back to a radius of 2 by the time you get to 2 pi. So this is like a cardioid that's got an extra loop in the middle of it. There's a name for this. We started out with a cardioid, and we could see that looks like a heart. Okay. The next one got a little bit tougher because it looks like a fan blade, but we call it a rose. And you look at it and you say, yeah, it could be a rose. What does this thing look like? My drawing skills notwithstanding. Here's what it's called. This is the reason I did it in green. I called it for years a limacon, but it's not pronounced that way. It's called a limacon. This is supposed to remind you of this thing in the middle here being a lima bean. Was that what it actually reminded you of? I don't know. But the reason that little loop in the middle is created is because that original graph doesn't clear the x-axis. If it had cleared the x-axis, if this piece wasn't there, then you would have ended up with just your regular old heart without that loop-de-loop in the middle. But because of that graph not rising high enough to clear the axis, that's how we end up with a limacon. And you can see in the equation now that if that number before the sign is greater than that number over here, then you're going to end up with one of those loops. If it's reversed, then you're actually going to end up with something that just looks more like a circle than anything else, because it's not going to have that loop in the middle. And in fact, it's not going to come down to the poles and create that heart shape either. All right, so we've got one more and actually a couple of funky ones to take a look at. And we'll do that in part 2.